Welcome to another session of knowledge representation on the web. We will be looking at ontology engineering today. And just to give you a recap of the course and what we've done so far, we've been looking at how to create and save knowledge graphs in so the syntax that we need to use. This is with RDF. We looked into giving meaning to the knowledge graph that you create using RDF-S, so the RDF schema vocabulary. And then we looked at all the different restrictions that you can create over classes and properties using the web ontology language OWL. What we still need to do is to learn on the practices on how to best build an ontology and how to query knowledge graphs with the Sparkle language. So for what concerns the ontology engineering is actually a field that is inspired by knowledge engineering and by software engineering, where the goal is to describe step by step how to best implement an ontology from a computational perspective. Just to answer generic questions that are often asked, and why should I care about ontology engineering? Ontologies are being used today by a huge amount of companies. So all the large companies, starting from Google, Amazon, eBay, Airbnb, they all use ontologies to represent their data, and knowledge graphs to store their data. So you will be seeing knowledge graphs more and more often, and you will be seeing advertisements for positions related to knowledge graphs more and more often. Now, the benefits of using knowledge graphs is that so these companies are now trying to move from recall in the first lecture we discussed about the difference between databases and ontologies, and why ontologies are allowed to express certain things or to perform certain actions that you couldn't do with classical databases. There's benefits including allowing communication between people, and not only between people actually, but also between software agents. So if you have applications that have been developed across in different parts of the world or by different people, they can interoperate because the standards, the vocabulary, the syntax that is being used to represent information is the same. So using the same syntax allow interoperability between applications. The knowledge graphs allow to reuse domain knowledge, so the certain information is expressed in a knowledge graph and it can be reused by different applications which might not know a specific domain that well. In particular, ontologies and knowledge graphs allow to explicitly express domain knowledge, so to formally represent it and express it. In particular, in these days where we have we discussed a lot about deep learning models, deep learning machine models, and where there is a necessity to make information explicit and transparent, knowledge graphs allow this to explicitly represent knowledge. Additionally, domain knowledge can be analyzed and unveiled if this is not known. In other words, what we can say is that the knowledge graphs allow to, and ontology engineering as a field that allow to build knowledge graphs allows to perform knowledge sharing, to share and reuse knowledge. So it's not really about I'm building the ontology, but it's about I'm formalizing knowledge in a certain way, and this can be shared with other people and reused with by other people. So the question is, how can we build a real ontology? There's lots and lots of ontologies. We are going to go through a number of examples in a while in the rest of the slides. You need to recall the definition of an ontology, which is an explicit specification of a shared conceptualization that holds in a particular context. This is a formal, the official definition. Sometimes you hear the word ontology and knowledge graph interchangeably. Knowledge graph is a more modern term. Before, we used to call them ontologies. There are some subtle differences. We consider, in this course, we consider that ontology is the terminology box and that the instances belong to the assertion box. By explicit, we mean formal and machine interpretable knowledge that is expressed through languages like RDF, RDFS, and OWL. So it's explicitly and it's formalized. By shared, we mean that it's open on the web. This is the main difference between the classical knowledge representation methods and the knowledge representation on the web methods. Open on the web means that the resources, the datasets, the ontologies that we publish can be reached through HTTP requests, and they are represented and retrievable. They're represented through URIs, and they are retrievable through URIs. A conceptualization is a set of instances, classes, and relationships. So there's a component of design decisions, which is inherited by the software engineering world. And a particular context, by context, we mean that when we represent an ontology, we tie this ontology to a particular domain and a particular task. So we do a certain commitment to that ontology. This is a very important definition, and it's the best one, that is most encompassing one when defining an ontology. There's the research and in the ontology engineering world, there are specific methodologies to build an ontology. The most common one is the work by Deborah McGuinness and Natasha Noy that defined a set of steps that you should always do when you build your own ontology. This is also important. As part of this course, you will have to work on building your own ontology. So the first thing you need to do is to determine the domain and scope of your ontology. So you need to restrict. You need to understand the context where you're operating. Remember that we said it's a conceptualization in a particular context. The first thing you do is that you actually start with understanding that context and understanding what is the scope of your ontology. Then the following thing you need to do is to consider reuse. Well, you might need to check if you decide to create an ontology about music, you might want to check whether there exist ontologies about music. And if there exist, you might want to reuse certain classes, maybe to reuse certain taxonomies, or to take certain membership or property information. Then the thing you need to do is steps that we've briefly maybe mentioned in the past lectures. You need to enumerate terms. So you just create a long list of all the terms that you want to include into your ontology. These can be classes, they can be instances, anything that you think is useful. You will have to do a choice between what you consider a class and what you consider an instance, but this comes later. So if we take this the music ontology example, I might start declaring singers or bassists, musical instruments, maybe terms that refer to action. A singer sings a certain song. Or a bassist plays the bass while the guitarist plays the guitar. Once we have enumerated these terms, we need to start defining a taxonomy. So what are the larger concepts and what are the subclasses that belong to these concepts? In the same way, you define the properties. So we enumerated a number of terms, and then out of these terms, you need to identify properties In our example, it could be place or things. Most of the time, it's easy to think of enumerating terms, and then nouns are usually classes or instances, and verbs are properties. Then you in step 6 you actually start defining classes and their properties. So this is when you start including semantics in your ontology. You need to decide what is a class. You need to decide what is its domain and range. So a singer is a class, probably a certain singer like Madonna can be an instance. A song can be sung by at least one member of the band. You need to, so this would be an example of a restriction. You start creating hierarchies. So for example, a duo is a subclass of a band, and so on and so forth. Once you have defined classes and your properties, you might already have certain instances, because in the terms that you enumerated, you might have decided that certain terms are actually instances and not classes. Sometimes the choice between what is an instance and what is a class is not that easy. It's mostly a modeling choice. It means that there's no right or wrong definition, there's a right or wrong decision in what is an instance of or a class. For example, I can decide that male and female are instances of the class gender, or I can decide that the class gender has 2 subclasses, male and female, and then I will declare all the members, all the people that I'm representing as individuals of either the class man, male or female. This is, again, it's a modeling choice. It really depends on the domain and scope of your ontology that you defined in step 1. Ultimately, the last thing you need to do is that you check for anomalies. So an anomaly is something that is not correct or consistent in your ontology. And if you recall from the last classes, this means that you need to run the reasoner, and you need to make sure that there is no inconsistency being declared. It's very common to run the reasoner several times, and not only at the end, but these are basically, you can do this, you can perform these 8 steps iteratively, which means you can go through the first round and then start again from number 1 and into several iterations. If we want to be a bit more technical, when you create an ontology, you need to start choosing a format. We recall from the first lecture, we looked at different format you want to save your ontology with. So we looked at REFS XML and triples. We recommended to use Turtle because it's more human readable. Ontology engineers have to document the ontology. So the point is that if you want to allow ontology reuse or knowledge reuse, you need to let the others know what is the content of your ontology. This means that you need to let them know what are the classes that are being declared and what are the properties that are being declared, maybe a few examples of instances. There's several examples on, there's several methods to do that. We will not discuss them in the videos, but we might want to have a look at these in class. You need to integrate other ontologies. Integrating other ontologies means that you maybe import certain classes and you declare classes as being equivalent class, or you maybe import members by declaring them as being same as other members. Finally, you publish your ontology on the web. And this obviously means that you need to have a domain name behind, and you can have support to how to properly choose a URI. This is just an example that the W3C consortium offers on how to create meaningful URIs or URIs that are syntactically correct. The last thing that you do is that you need to evaluate your ontology. And the way you evaluate your ontology is by determining the adequacy. For example, you have experts and you ask them to evaluate whether your ontology is able to represent certain knowledge. Or maybe you have a downstream task, and then you can check whether your application that is based on, that is using information from the ontology, and how does it perform with an application that is not using such information. Just to go through a small list of tips and mistakes that you can do. Every statement that you do in the ontology is a commitment to the view of the domain, so the context where you are operating. And it's very common that you perform overcommitment. This means that you are making the ontology expressing statements that are too strong. So you might be careful. What it means is that when you express certain restrictions, you need to be careful with what you are expressing, because if you overcommit, then you are more likely to run into inconsistencies. When you represent an ontology, people tend to have a tendency to try to represent as much as they can. There cannot be a global ontology. There's not an ontology of everything. Ontologies are dynamic, so information changes over time, and so do ontologies. Additionally, every person can have a different perspective on the domain, so you cannot really pretend that you represent the domain with a general overview. Ontologies live in an open distributed world. This means that contrary to the database world, that where databases operate in a closed world assumption, where anything that is not said is certainly false, ontologies operate in an open world assumption, or OWA, where things that are not being stated in the ontologies might be false, but might also be true. So this is an important distinction, and your reasoner will take this into consideration where inferring new triples. The best choice that you can do is to choose the minimal ontological commitment. So especially with the modern knowledge graphs, which are huge in size. So we started years ago with small ontologies with hundreds of triples, but now we are talking about knowledge graphs with billions of triples. It's best to reduce the amount of restrictions that you create in your ontology. So prefer domain and range instead of using complex class restrictions. This doesn't mean that your ontology is not good, it's that you are simplifying the commitment that you are creating. The same with domain and range is that you need to be careful. If you restrict too much a property, then you might risk that you are reducing the type of representation that your ontology can, the modeling of your ontology. So if you say wine has a color and therefore the property has color should have domain wine, well, if tomorrow you end up adding a new class which also need an S-color relationship, you will have to change your ontology. It doesn't mean that you cannot change it, you can actually change it, but it mostly means be careful when declaring domain and range. Universal restrictions are, we looked at some values, all values from, they do not work very well as necessary and sufficient conditions, so you need to be careful with what you express when you restrict your classes. And you need to run the reasoner all the time after every ontology change and update to check consistency of your ontology. So every time that you add a new triple or maybe remove a triple, make sure that your ontology is still consistent. The libraries that we use and the programs that we use in our course allow to run the reasoner very easily and to check consistencies in a very short time. Make sure you always save your files in a way that you are able to read it, especially if you read them through Turtle. Additional tips: try to make a list of classes, properties, and instances you're planning to use. Define each class. Make sure that you specify necessary and sufficient conditions, but also remember that they don't work well when they don't work in all occasions. Use disjointness and complementarity of classes varying not that often. So again, these are only tips to try to reduce the commitment of your ontology and to avoid incurring into a reasoner that says your ontology is absolutely inconsistent. And then it's very useful to test, to create a test instance. So an instance of when you create a new class, you can create and you give certain restrictions on this class. It's very useful to test this class, whether it's working, whether it's not generating inconsistencies, by creating an instance and running the reasoner.